Hello. How's everybody doing? Pop over here real quick. Hey, back to the blackboard. So multi-stream? Yeah. Just like doing a bunch of stuff. I don't know if that's what that means. That's what I thought it meant. Maybe it's wrong. I do want to game, but gaming means I have to do probably at least one control volume analysis problem, which maybe kicks my ass. It's fine. It's fine. I'll just find a steady flow one, and it should be fine. Then we get to have ddt equals 0. But speaking of that, I'm gonna really quickly hop through this stuff to clean up what we were doing last time. Just grab these coefficients, which I'm realizing I probably could have just done earlier. I just have to throw this real quick. But while I do this, I hope everybody's doing well. How are you guys doing? Anything cool happen? I know Umbra, we were at Miku Expo, which is super cool. I don't know if Miku is ever anywhere that I am. I'm gonna be real. He probably does a show in California somewhere. At some point. It was so hype. Oh, she's so fun. I feel like her fans are like good too, you know? Oh yeah, I forgot I got these weird like eighth values. Oh, I'm gonna leave them as eighths. I did kind of absolutely demolish this exam though, so I'm enjoying that I did well. But okay, 0.8125 is 1/8, right? No, maybe? What's 1 divided by 8? 0.8125. It's some like common fraction. Such a nice experience. People upset about the screen, but they made insane use of it. Ooh, 13/16. That's so cool. Okay, I don't know. I know people are like a little about, cause I like, you know, VTubers, like people are like, VTubers, they're it's so boring when they just are around. But I'm like, I kind of like it when people do interesting stuff, you know, on a screen. I think it's pretty cool. And Miku, like, that's Miku's whole thing, you know? What else are they gonna do? They're not gonna get like a wraparound screen or something. A negative 13/16. This one feels like it could possibly be right. 2/16. Just with how, like, you know, clean the answer is. The coefficients are a little weird, but... It's not because it wasn't the hologram. Oh, the hologram is way different than what they pulled off of the screen. Oh, wait. Well, I know Miku's like a hologram. I don't really know, like, how they do that, though. Is it, like, just a light projection thing? There's way more extra animation. And I can't wait till we get like those volumetric displays. I don't know how those have been coming along. I saw them a while ago. I'm assuming that they don't scale well though. They're very little. Yeah. Maybe that's what they do for it though. 3D volume display. Volumetric display concepts for the future. Voxen photonics. So cool. Or, you know that guy who does the, I don't know how there's a certain, optics effect that you can achieve by, like, putting a computer screen and then, like, reflecting it, and it looks like it's projected. Is that how they do it? How do they make Miku? How does Miku get projected? Projector... Let's see. This is... I don't know when this was posted. OLED screen technology. Double-sided projectors. How does Miku work? Projected onto from the back. Known as rear. It's Pepper's ghost. Oh, it is Pepper. Oh, wait, no. It's similar. It's similar to that. A piece of plexiglass, and they project onto the... Huh. It's cool. Optics are pretty cool. I mean, I think... I don't know a lot about, like, display tech, but we're getting into this space where it's like... That stuff is pretty good. I know it uses glass. It's like a box. Oh, I see, I see. I don't like this answer, but I'm just gonna go with it because I kind of don't want to deal with it, and that's how math works sometimes. Let's see, 1, 1, 0. Oh shit, no, it's a 3x3. Whoopsies, teehee. Reuse this one. There. Maybe if these coefficients come out nice, then I'll be like, yeah, I trust it. That's my toxic trait. I don't know. I need to check my work more. But usually, if the numbers work out well, then you're like, ah, I'm doing it right. Oh, they worked out well. Have you ever done the hologram trick with your phone, with the little mirrors in your phone? No, I actually don't think I have. Shoot, I have to write all this out again. But I think that's the Pepper's Ghost effect. Probably. I've seen other people do it. Imagine that with big and multiple projectors. Oh. That's so cool. Man, why can't I... Well, I don't do optics. That's more physics than engineering. But it's like, why can't I be the person, like, one of the engineers who, like, has to make Miku real? That would be awesome. It's like, I don't want to build... I don't want to blow stuff up. I just want to make Miku real, guys. How do I explain? How do I explain that that's what I want my job to be like? I'll show in... Oh, glasses? Yeah. Oh, yeah, yeah. If you have an example of it. I'm gonna leave a star on this. Wait. Let's do... I'm gonna leave a star just in case. I'm gonna say... Go fish. Might be whack. Say... Cofish. Multiple... Might be whack. And then... The other thing I was worried about for this was the... Lots of shift, lol. Maybe... mistakes. More for notes for me. Like that, and just imagine big projectors in a box. I think it's a box. Let me see. I'm interested. I'm intrigued. Oh, yeah. Oh, that's awesome. I think it just depends, like, about how you're setting up the experience, I guess. More than if it's a hologram or not. But I can imagine. I understand. I wanted to see a hologram, but I think you can have a cool experience either way, and you can definitely have a bad experience. Like, it just because it's a projection doesn't mean that it's instantly cool. Whoops. Why? Oh. Wait, what? Oh. My professor was so nice when he was grading my midterm. He put a smiley face next to the score, which I like doing when I grade people's stuff. My book just fell over. Okay. I started doing this problem. Stop sliding everywhere. Okay, so this is the piecewise function. This is just, I'm jumping right into the Laplace of it because, I don't know, I don't have space. I'm gonna nab the integration by parts stuff we need. Actually, I guess I don't even really need to do integration by parts for the first one. We can kind of just look at it. Or, well, not the first one. The first one we really don't need to do integration by parts. But, give me 2 times negative 1 over s e to the negative st from 0 to 1. Then plus e to the negative st, we can pull that out. This is going to be negative 2 minus t over s. Did I forget that? Oh, I did forget that. Minus s, and then minus 1 over s squared. Oh. Yes. That's from 1 to 2. This one I'm gonna have to, I can't just like smoke and mirrors my way out of it. So 2 times 2 times, oh no, sorry, negative 2 times 2 minus t. Honestly, they made the big ass dot matrix screen work really well. I think there was only 1 or 2 times when I was like, oh, that was it's a screen because the light shining off the back without the lights around. Oh, so it just looked like not even a screen. See, that's what I'm saying though. Like, I feel like you can get, it's more about how you use it versus like the tools themselves. Although, I think the thing with a screen is like viewing angles are gonna be probably a little harder to work with. That's just 2. Oh, I did not get the negative on that one, but that's fine. Bam, bam, bam. Plus, minus. An LED, not like a traditional screen, so it was perfect at every angle. Oh, that's awesome. That's so cool. You know, I really think like one of the things I've been thinking about, because I want to actually try and do some lectures this summer to post on YouTube, and I was thinking about kind of what problems to give and stuff, and I swear this is related to that. But it's kind of interesting to like, you know, whoops, sorry. Probably really unfortunate auditorily that for a second. And it's like you learn optics in physics too a lot of the times, and it's kind of like, well, you know, what am I gonna do, like make a thing bigger with, like magnification? Why does this matter? But it's like, if you put it into that context where it's like, oh, you can Miku, then people go, wow, Miku. Do a lecture on how to get back into math for adults who don't do math. Oh, I could totally do that. I want to do one. My first one I want to do is, like, how to, like, understand trig as a tool to use and not just like as a math thing that you learn. Because I think the thing that I find the most overall with any like within engineers or within people who are doing stuff is that they don't have a very conversational relationship with trig, and it just makes things so much harder. Negative what is this? 2 minus t squared for s. I think I can just, yeah, and then plus, that one's gonna be plus actually 2 minus t over s squared, and then minus over s cubed. Oops. From 2 to infinity. I'd love to do like what kind of math? Like calc stuff, or I feel like it kind of depends on what you're trying to use it for. Or just like, because it's interesting, like the way that I think about teaching physics and stuff, or because I want to do fluids as one of my first ones that I want to lecture on. It's actually like not super focused on the math. It's more focused on the concepts that we're using, and then like you can either do it, just think about it, understand it conceptually, or you can actually like do the math and go that like second step further. Lecture on cogs fluid. It was funny. Me and my friend were thinking about starting a club, like a maker club, and I was like, oh, it'd be so cool if we could, there's a bunch of like screens, you know, ad screens around campus. I was like, okay, what if I like made some like funny bumpers like for this club, like ad bumpers, like Adult Swim ones, and I was thinking about making one that was talking about cogs fluid. Because like, what like kind of weird things are people gonna be like, oh, that's kind of weird, what are they talking about? I actually don't know anything about cogs fluid. I also thought it was NDA. I'm not sure if I'm remembering that correctly, but I thought he got in trouble for it. Let's see, when t is 1, we get -1 over s, e to the negative s. And then when t is 0, we get, I guess, plus 1 over s. He doesn't talk about it? Didn't talk about it? But I saw that on his Twitter and I was like, oh shit, this guy's fucked. Okay. Okay, so for when t equals 2, we get e to the negative 2s times, well, this will be 0. I guess negative 1 over s squared. And then minus, when t equals 1, we get e to the negative s times negative 1 over s minus 1 over s squared. I guess I can just do that. That's fine. And then this one should be easier. So the first term is just 0. We like that. E to the negative 2s, sorry, times, wait, when it's infinity, yeah, it goes 0. And then this one, when t is infinity, these just kind of bork out on the top. Wait, is that? No, when t is 2, those are both 0. What am I talking about? But it's a negative, so this will be positive. Now, can I simplify anything at all in this? I feel like no. I mean, I can, this kind of sucks is the thing. What am I supposed to get? Okay, one of these is gonna be, like, 1 over s, essentially. But why is it shifted? Oh. I guess maybe... Okay, I guess I just factor out all the 1 over s's. 2 times e... Nope. Where's my other 1 over s? Oh, here. E to the negative s? Is that even a shift? What is that a shift of? -1? I guess? No, it's a shift of... That's so weird. Ugh. Oh wait, there's another one. Oh wait, does that cancel out? Wait, 2 times negative s e to the... Also, this should be plus. What am I doing? This would be... Okay, 2 minus 2e to the negative s, and then plus e to the negative s. Okay, sure. I don't even know. That's kind of weird. I don't like that. I feel like that's very wrong. It's okay. It's whatever. And then I guess we have 1 over s squared. E to the negative e, negative 2s. Plus e to the negative s. Means nothing to me. These are just numbers. Ugh. 1 over s cubed. 2e to the negative 2s. That's so weird though that it's like multiplying e into it, because if you have e in there originally as your s, that's... No, that makes sense. That's a shift. This one is right, I think. This one is right. This one, I don't know what's up. This and this are weird. I'm just gonna leave it, whatever. 2 and 3, or 1 and 2 terms. Weird. Oh, what was I doing here? Oh, I was having the same kind of issues. Ugh. It's so icky. Okay. Did I integrate that right? What the heck was I doing here? I can't even tell what I was doing. Okay. I was getting that. Okay, so I did the 2, and then I plugged in... Was I trying to do this all in one step? What the hell was I doing? I think I need to get rid of this stuff. Let's do that. I think I can tell why I got it wrong, because I don't know what I was doing there. This one can go all the way down here. Okay. We got space now. I'm just gonna like maybe kind of just like okay. No, I got scared. I'm gonna do this. Kind of give myself a little. I don't want to waste too much space on that. Okay. I need to integrate this. Equals 2 times... Okay, what is that up there? You guys can't see it, but I'm referencing that table there. So it's negative 1/3 e to the negative 3t times t cubed minus... Is that right? They're like all gonna be minus? That's so weird. Okay, oh wait, I can pull out the e to the t cubed. Let's do that first. Sorry, e to the negative... Oh, negative 3 minus s, actually. T. And then we have t cubed over negative t cubed over 3 minus 3t squared over 9 minus 6t over 27 minus... I can't help but feel like I got that goofed. That feels goofed. Oh, I did the same thing here. Oh, it's not over 9. Urgh! It's 3 to... boy, that's... yeah, that's rough. Okay, there we go. I was like, that seems wrong. I feel like there should be a plus though, so this one is gonna be plus. Oh. Wait, shouldn't that be minus? Maybe I got it wrong here. But it should alternate, it shouldn't always be minus. Yeah, it should be minus there. That's wrong. I don't really want to fix it though. I'll put a little oops. Eto bleh. That's fine. And then minus 6 over 4th. Evaluated from, I don't know what this is from. 0 to infinity? Oh, we love that. Makes my life easy. Oh yeah, it's gonna be so nice to work that out. It's gonna be 2 times... Oh wait, did I do an extra minus? I think I did. 2 times -6 over -3 minus s to the 4th. Which, does that check out? Let's see, 2t cubed, Laplace transform. Why does it have a shift? Why is that shifted? That probably shouldn't be shifted. I don't know why. Was I just not doing the right one? What was I using this for? Literally, what was I using this for? Well, okay, so, I did all that, and we don't need to do any of that, so don't worry about that, chat. Don't worry about that. Don't look at that. I mean, it would have turned out nice, but I don't think I need this. Why was I doing this? I just straight up don't need to do that. I need to do t cubed, 3t squared, 6t, 6, 0, and e to the negative st, but that's just like negative e, negative 1 over s, e to the negative st, 1 over s squared, e to the negative st, negative 1 over s cubed, e to the negative st, bam, bam. Oh, I need one more. 1 over s the 4th, e st. Plus, minus, plus, minus. Okay. I could probably just go ahead and evaluate it, but I don't want to do that. That would be like too many steps. Negative t cubed over s. Okay, so it is minus every time. That's weird. I mean, it's not weird, it's just a little weird. That feels a little strange, but it's okay. Alright, there we go. So that's gonna equal... So, oh my gosh, my professor draws infinity like this. So he makes like 2 circles like that, but sometimes he doesn't finish it. He's just drawing like balls. I'm like, dude, that's either an omega or it's like you're drawing a little funny pee-pee. I have to be professional, but also I have to be like, you're drawing a funny pee-pee. Negative 6 over s to the 4th, e to the e to the negative... Oh, that's just 1. Teehee. Now that's correct. That's correct. Is it negative? I don't think it's negative. I don't know why it's negative. It should be positive, I think. Did I just flip this sign? Okay. This will be negative. Is it supposed to be negative? Am I, like... I could be being silly, Billy. When you take the power rule, you bring the power down. Or sorry, we're integrating. You bump the power up. And if you were to integrate that, yeah, you would bring the negative s. So I don't know. It probably shouldn't be negative, but what am I gonna do about it? Okay. I need that e. E to the... Oh, that's just an easy one. It's e to the negative s plus 2. That. And then if we integrate that, we get 1 over s plus s negative. Yeah. I really need to buff up my integration. TBH. I can't wait to show the this cosine thing is gonna be bad, I'm guessing, but I can't wait to show the all the stupid plane integral that I spent like way too long on. It turned out well though. I mean, I got a number. I don't know if it's the right number. I have to check it with the Reynolds transport. But okay, so this will be 4 times. I don't know, what is that? See, when t goes to infinity, the whole thing's 0. When t is 0, we get negative 1 over 2 plus s. I'm definitely doing something wrong. It should not be negative. I don't think. I think it's because s is supposed to be... No, s is not supposed to be negative. I'll have to check that. I'm sure it's something very embarrassing that I'm doing. Okay, do I have space to fit? Not really, but I can try and squish it. Yeah, we can squish that in there. What is that? 1 over s? Okay. E to the negative st of negative 1 over s. Oh no, we're fine. Look at that, we're so fine. Now, what we're not fine about is this 0 to infinity. I don't know if I have to use L'Hopital's rule. But that wouldn't actually help, because... Oh, wait. Would it? It would just go to 0. The 1 over s wouldn't actually help at all. They're negative, so... How the hell do I integrate this, evaluate this integral when I have cosines and sines in it? Like what, cosine of infinity? That's not a thing that exists. Oh wait, but for infinity, it's gonna be... Oh, wait, never mind, we're fine. Because it goes to 0. Oh, we just narrowly... Oh, that's so awesome. Okay, so sine of 0 is 0. So it's negative 1 over s? That's not right. Why is it negative 1 over s? That's not right. That's so not right, but that's okay. Yeah. Oh, well, it should be... Oh, I know why. Because all of these are like minus. That's why they're plus. It's minus, because they're on the 0. Okay, 1 over s is the Laplace transform for like 1. I don't know how we got that out of cosine. It should not be that. But, you know. Oh, wait, because I didn't do 1 over... Wait, no, wait, we're chilling. Wait, we're chilling. I just didn't divide it by 1 over 1 plus s squared. Or, sorry, 1 plus 1... Yeah, 1 plus 1 over s squared. 1 plus 1 over s squared. Oh, we're so fine. So 1 over s divided by 1 plus 1 over s squared, or I guess 1 over s times 1 plus s squared? Okay, why is it backwards? It's supposed to be this on the bottom and this on the top. How did I goof that? How did that happen? Maybe I have to multiply everything by that to like kind of even it out or something? Hmm. It's close. It's close. If I was multiplying this, essentially I'm multiplying this by 1 plus 1 over s squared. Which I guess this part equals 1 over s plus 1 over s equals, wait, we're close. Oh, if I just multiply it by s over s. Oh, you know, just like that. There we go. Never mind, we're awesome. It's all right. It's all correct. Wow, I'm actually quite pleased with that. I didn't think that was gonna work out. Hey, and that means we can do we've done the recursive integration by parts. Everybody's favorite part of integration by parts. It looks like I just, like, spilled a glass of numbers all over the page. Here, look, we can even give this some breathing room. Look at that. Wow. Well, I think that's actually kind of done. I think that's it. Oh, no, that negative is okay. We figured out the negative issue. It's just not an issue. Wait, it is an issue. The issue gets fixed. I actually don't think it matters because it would get fixed either way. Yeah. Also, I like how I just didn't carry the negative. I was like -1 times that, and then I just didn't I didn't do that. So let's fix that real quick. Okay, minus this plus that minus this means we have minus this, plus this, and then we have minus, and then plus. Okay, easy. Awesome. For that. And I think we got the Gauss. This is so beautiful. Gaussian type heat. I feel okay. I don't feel great about this, and I don't feel great about this. But I don't feel bad enough to, like, really care. So, let's do some... Oh, sorry, flashbanged you. Let's do a little bit of temperature. Okay, this problem is making me actually kind of lose my mind. But, you know, what are you gonna do? That's actually maybe the quickest problems that I've had in a long time. Well, these mate ones are actually also pretty quick. Alright, let's see. Thermal expansion stuff. So, materials are really cool. This class is really cool. I don't know, my issue with it is that there's so much stuff that we're doing, and we're not using it in applied enough ways. Like, it's sort of applied, but when it's applied, it's mostly like civil engineering type stuff, which is like another class which we do. But none of them are really applied in any meaningful way, so it's kind of like, I feel like when I go to use all this stuff, I'm gonna be like, I know what this stuff is, but I don't know actually how to use it. So okay, a rod of brass, 0.35 meters long, is heated while its ends are maintained rigid. Determine the type and magnitude of the stress that develops. Assume that at 15 degrees Celsius, the rod is stress-free. Okay, type. I don't really know what they want me to say, but I'm gonna say compressive. It's a compressive, I mean, it's uniform, we don't really care about that. Longitudinal. like stress from thermal expansion, I guess? Which, I don't know. It's kind of whatever. Okay, magnitude. Okay, magnitude. So we want delta L equals alpha delta T times L. And that's also equal to FL over EA, which is also equal to stress times L over E. So stress equals alpha delta T times L times E over L equals alpha delta T E. So the length doesn't matter, actually, which I guess kind of makes sense because stress is a per... It's a little bit more about per unit type stuff. Like, we have an alpha, which is a per unit property, and we have a temperature difference, and we have elastic modulus, which is per unit, so it's kind of interesting that the stress doesn't change. Although our beam is like this, it's not, you know, like we're doing a beam that maybe gets thinner. It's an extreme example. Or like maybe if we had a taper, you know, that went off then into a straight beam. These ones we would have to... Those would be indeterminate axial loading problems, but... Okay, so it's brass, and we're going from 15 to 85, so what is that? That's... 10 to 80 is 70? So sigma equals 70 degrees C times... I do not know the alpha for brass. I had the table up at some point. What is this? That's the coefficient of thermal expansion. Here we go. Let's see, brass is 18 to 19, 10 to the minus 6 meters per meter. Let's say 18. I don't know. Well, I mean, I guess maybe we'll be conservative, 19 meters per meter, degrees Celsius. Or, sorry, times 10 to the negative 6th. That's pretty important. If it was 19 meters, that would be... We would never build anything out of brass. Or, well, we would build very specific things out of brass, I guess. And the elastic modulus of brass. I don't know the elastic modulus of brass. Does it tell me? Nope. Fine. Uh, 97 gigapascals, sure. Okay, what is this number? What are we feeling? This is gonna be a big number. It's a lot of stress. But I mean, stress is in pascals, so, you know, it's not that crazy that it would be a large number. Oh boy, that is a large number. Okay, it's not like, okay, so 0.129 gigapascals. What is the stress magnitude if a rod 1 meter long is used? It's the same. Which is cool. If the rod in part A is cooled, what type and magnitude of stress results? Okay, I'm assuming that they mean then maybe the type is tension. I guess I don't really know tension. Like tensional? Longitudinal stress from thermal, what's like the opposite of expansion? Retraction? Shrinkage? What is that, 15 to 15? Negative 30. I will say, I really love stuff like this because it's such a simple model, and you can just, like, kind of plug in a bunch of stuff to it and try out a bunch of stuff, and I really, really like that for design problems. Like, just the idea of that, you know? It just scratches an itch for me to be like, oh, I can find out so many different numbers. Okay, I'll do this one in megapascals instead. Oh, I guess this one would be negative, huh? Because it's a tension is positive, so. This one was really getting me. I don't really know why. This top one. So to what temperature must a rod of tungsten and a 1025? I also learned what 1025 means. It means that there's 2.5% or 0.25% carbon in the steel, which that's pretty cool. We got to temper steel, which was actually not as scary as I thought. It was very hot though. It was 700 degrees Celsius, 727 for austenite to form. Okay, so we have a 1025 steel plate with a hole, and wait. Okay, yeah. What must both of them be heated in order for the tungsten rod to just fit into the hole? And so, okay, I was thinking Poisson's ratio, because our alphas come from, they give us longitudinal changes, but they don't give us diametral changes, which is what we need. And that would be, to get from longitudinal to diametral, we need Poisson's ratio. And so this is the equation for Poisson's ratio, where this is Poisson's ratio. Poisson. So the change in R is equal to R times the change in length times the ratio. And we have the change in length equals alpha delta CL, which is fine. So R equals R over L, that just comes from here, times alpha delta TL. These L's cancel. Then you get R equals alpha delta T dr. And so the question is they both have different rates of expansion. And they're both going to expand outward. So one is going to catch up. And I want to say, I don't remember which is which. Let me write some coefficients down here. Oh, I have a coefficient there. So let's say alpha steel. Let's say it is. So alpha steel equals 12.5. Nope, that's the V. Wait, is that true? Wait, maybe I didn't put minus. Oh, that might be why. I don't know if I put the minus to the milli whatever for the units. That's probably it. Because I was getting a very small number, and I was like, that is not correct. So maybe let's do that though. So alpha steel is the one that they have here. I guess I should find 1025, but we'll see. Steel. They do not have a, let's see, 1025 steel. What would we got? CTE. Mechanical properties. Tensile strength, yield strength, elastic modulus, Poisson's ratio is, I mean, to be conservative, we can say 0.3. Wait, they didn't, oh, thermal properties. I was supposed to say, they literally didn't give me the CTE. Coefficient of thermal expansion. Here we go. Metric? What the heck? What is this? Why would they give it to me like that? I don't want that. Probably say coefficient of thermal expansion. Wait, this is just... Oh, view data? No, don't do that. I'll search for coefficient of thermal expansion. I'm sorry. Okay, yeah, it's to the -5. That would probably mean why I was getting like a millionth of a number. I was like, if it changed 1 degree, it would like explode out in expansion. That's clearly not right. So I'm just gonna multiply both of these. Oh no, I can't multiply both. Oh, it's fine. To the -5th, I think it said. Wait, but it also says coefficient of thermal expansion is 1.23. What is this number? What was it? Oh, 1.2. Oh, maybe it's 10 to the 6th. Wait, 10 to the 5th. Ah, 1.25. Okay, yeah, that's fine. This is 10 to the 6th, and then this one will also be 10 to the 6th. So I actually probably could just, like, do it out. Let's see. Not do it out. I could probably just multiply the whole thing by it, was what I was getting at. Okay, we got 1.25 times 10 to the -5. I also got a negative number, which I think is maybe wrong. But we'll sort that out later. I'm worried this is gonna be like 300 degrees, and that would be kind of bad, but also, I mean, maybe not the worst, I guess, now that I think about it. 300 degrees is not terribly a lot. Okay, it's this. Wait, that's a negative number. Wait, no, it needs to be a... Is it gonna be negative? It's gonna be negative. We're fine, the negatives worked out, let's go. Wait, but it needs to be a negative. There we go. I'm kind of tripping. Okay, here we go. 5,486 degrees, obviously. Okay, that's wrong. It's definitely not right. 5,000? Well, now I've gone too far in the other direction. It's too big. Okay, I should, Let's do a lot of things out here. Okay. So this is the constitution, or the constraint equation that we're working with. So we say that the change in the steel... Okay, wait, does this actually make sense? My constitution might be wrong, and that's why I'm getting it wrong too. I was saying that the initial radius plus the change in the radius... Oh yeah, the change in the radius for the steel has to equal the radius plus the change in radius for the tungsten. So, yeah. So we have radius steel plus alpha, I'm just gonna call it S, it's gonna be faster for me to write. Plus alpha S times delta T, that's the same for both of them, times VS equals R tungsten plus alpha tungsten delta T times V tungsten. Easy. Now we solve for T, so RS minus RT equals delta T I'm actually just gonna, I'll just solve it here. Delta t equals, okay, I'm gonna use this one. So RT minus RS over, if we scoot that onto the other side, we get alpha S VS minus alpha T VT. Okay, cool. So that's gonna be, what is that gonna be? Let's see, what is the, so tungsten is the 15.025 and steel is the other one. Divided by 2, and I'm gonna multiply the whole thing by 10 to the negative third. If I can. Well, not because I can, because it's millimeters. And then we need the actual coefficients. So for steel, it's fine. We'll just be conservative. We'll just say it's like 12.5. And this is in 10 to the negative 6th, I believe. Yes, 10 to the negative 6th. What did I say? 12.5 times 10 to the... I'm going to pull out the 10 to the negative 6th. And I don't remember what the Poisson's ratio for steel is. It's fine. Oh, it tells me. 0.29. And then minus the alpha for tungsten, which is probably not going to be a ton, but maybe it is. 4.5. That was correct. It's not a lot. And then the Poisson's ratio for tungsten. I spelled it wrong. 0.28. Okay, about the same. Nice. Okay, let's hope this gives us better. So this will be 10 to the third on the top. Okay, so we get 0.0125, and then... Oh, this is nice, because I don't have to actually, like, worry about the... Okay, this... divided by this... Oh, hey! Oh my gosh. Okay, that also seems wrong, but seems a little less wrong, maybe. Did I forget an elastic modulus somewhere? Why did I have elastic... Wait, no, I didn't have elastic moduli in here. Well... I don't know. I mean, I got 5.2. I kind of don't think that's right, but maybe it is. I think I'm missing something somewhere. Radii, that's fine. Drugs. Yeah, I don't know, that seems like I got the numbers right. Well, whatever. It's done, and I think... Oops, whoa. Sorry, I hit hiccup. Oh, I don't want to do that right now. Okay, wait, we can do a fluids problem now. Oh god. Should we do this one? What do you think? Should we do this one? Oh, also I realized I don't need to put area vectors where there aren't any velocities. I was labeling every surface of my control volume, and I was like, I need to do this. I guess I don't really need to do that. Okay, let's go for it. Okay, we start with the analysis. Let's just, I'll do 1, and like, if it's like really bad, then we'll figure it out. Okay, so conservation of mass is the first thing we say. And so for, okay, water flows steadily. Ah, assumptions. So we need 1, steady flow. We like that. That's like our best assumption ever. That makes my life like actually easy. Oh, like a pause. Okay, so we got steady flow. We like that. We're evaluating them. Okay, let me read the problem. So it flows steadily past a porous plate as shown in the figure. Constant suction is applied along the porous plate AD. Okay. The velocity profile at section CD is given by the following expression, where the values of u infinity and delta are provided in the figure. U infinity. Ooh, okay, sure. Evaluate the mass flow rate across section BC. Okay, section BC. So I guess the whole thing. So mass flow rate is defined as, it's, I believe it is, oh. Okay, so there actually might be a velocity there. Oh, I don't know actually, that's a little interesting. I guess we can't say for sure if there is or isn't, so maybe I just will draw a velocity vector there. My intuition was correct. It was not correct. I don't know, let's just say it goes up. Who knows? Maybe it does. Maybe it's 0. I don't know. Okay, so for this, we're gonna have 0. We're conserving mass, so that's our whatever it is. What is it? Our system change rate thing. Really great explanation. So ddt of the control volume. I'm trying to remember what this is. I don't know. I vaguely is not the, remember it. I don't remember the exact thing. It's just rho dv. Okay. Oh wait, I was so close. I was close. Rho dv plus, and then we have like the sum of our like. Or I guess I don't really need to do that. Control. I'll pop it out. Dude, we'll do all of them. Why not? Okay, so control surface 1. We're gonna say it's, looking at my notes. It's rho 1 d1 dot da. da1. And then plus control surface 2 rho 2 v2 dot da2 plus control surface 3 rho 3 v3 da3 plus control surface 4 rho 4 v4 dot da4. Okay, cool. Rho dot plus give j equals 0. Oh. Are you saying J? I'm trying to figure if you're saying J component or not. Well, so we do have some stuff that equals 0. This is going to equal 0. That's steady. We like that. We have some stuff that can come out. Well, okay, what are we given? We're given, like, velocities. We're not really given any, just, like, quickly glancing, we're not given any, densities. We're not really given any information about density either. Although, this is water, so we can assume it's an incompressible flow. Which means that our density is going to be the same throughout. This is the continuity equation that shows up all over the place. Oh yeah. Yeah, this is specifically like it's Reynolds transport theorem. It's just like big chunky boy that you use to basically just do everything in control volume analysis. It's kind of fun. So we can just get rid of the rows. So they can come out and they can be divided out because they're all the same. And then I'll just like, I don't know, yeah. Because if it's the same throughout everywhere, it's water. We like water. What else can we do? Okay, well V1, we know that V1 is... Okay, which one is our V1? This one is our V1. This is not, for sure not something we can pull out. It looks like they're saying this V is negative 0.2 meters per second squared, millimeters per second squared. So, 2 and 3 are uniform, so we can pull those out, which is nice. But we should do the dot product stuff first, I guess. Well, we can rewrite. Okay, so we rewrite this, we get control surface 1. Okay, so let's see, V1 and DA1, are they in the same direction? Why did I write V3 here? V1, DA1. Wait, what? No, I'm dying. There we go. 3. Jeez, okay. They are in the same direction, so that'll be positive. This one's going to be positive as well. This one is going to be negative, and this one is going to be, well, I guess we kind of don't really know, but we'll say that it's positive. Because, why not? We get V, DA. I guess say V1, DA1. Plus, and this one is just going to be, it's really nice. We get to just say V2 times A2. And then plus, oh, because this is going out. Yeah, we might have to have, there might be a mass flow. I don't know, evaluate the mass flow rate across section BC. It's a little, I don't exactly know if we have to evaluate, because along this surface, I don't know if there would be any flow. Well, there probably is. There might be. I might need to use my control volume differently. But I also... Because I do know this is a function, so it's not like I can't like say like, oh, I want to do this from 1 millimeter, but then, you know, that's a little... It's a little weird. Okay, so we got that one. V3 is going to be a similar thing, so V3 times A3. That's a minus, though. Important. And then plus... We don't really know if the velocity is the same, but that is going to be V4DA4. So we've gotten rid of all our vectors, which is nice. Oops, I also didn't write the control surface. There we go. Okay, got some stuff to work with now. And we can also just chuck the control surface 1 equation in there, which is 3y over h. I'm gonna name this to h. No, I should use it. I just don't like I don't like writing it. Delta u. Okay, so what is this? 3. I'll leave the integrals open. We can just do 1. Do they give us a depth? Let's see, it shows width. Okay, W. We'll just do it as W. We won't plug everything in yet. Okay, so 3. Wait a second. So u divided by u infinity equals this. So u equals u infinity times that. U infinity is just a given. I mean, it's a value that doesn't change, so we'll pull u infinity out of there. Very interesting. 3y over delta, which is a constant, minus 2y over that 1 point. Okay. Easy integral. We like it. Incredibly easy. And then our dA in this case is going to be dA1. I'm gonna assume it's a like A, B, C, D is it is a channel. Just to say that. I don't think it necessarily says it, but it gives us a width, so. I might need to assume more of it as a channel, but that's fine. dy times width. And then plus v2. So v2 is our out one, that's given, but u infinity is the other one. So we can pop that in. Actually, these areas are going to be the same. This is going to be delta w minus u infinity delta w. Wait, nope, I lied. That's lw, not delta w. And then plus, okay, we have to, I think this might just beat the mass flow rate. I think this is m dot. I mean, I don't have to cancel out, wait, yes, God damn it, I want the mass flow rate, so I have to put all the... Right, because density times a volume, fuck. Man, wait, how do I get rid of the other ones then? I don't want density in here. They don't give a density. Well, I mean, maybe they do. I guess I could say it's water. But that's not super... I'm gonna put a note there. So we want mass flow. Want mass flow. But also don't want density. Well, that's pretty clean. So then we just have to integrate that. And that, I guess we just say that that stuff equals our thing. And then that's our known. I think that's what they mean by saying mass flow over across section BC. I'm not sure if that's what they mean though. The mass flow rate across section BC. It's like section. Well, I guess it says, oh, okay, well, I guess it says constant suction is applied along the porous section, AD, and they don't mean like the full bit there. That's probably what they mean. They probably mean this. It's kind of chill. I mean, these are all knowns that we have, so it's not like we can't integrate this. So let's just do that. That's yellow. Do this. Oh, I do have to integrate over something. 0 to this. Oops, that is not how you write that. Yeah. Yes. Yes. Okay, so we get 3 over that, y squared over 2, minus 2 over this to the 1.5. Y to the 3.5? 2.5? over 2.5? W. Wait, let me pull the W out front. Then V2 we're just given, so that's still fine. Leave that. Minus, this is also a given. Yeah, I mean, I feel like that's just it. I mean, 0. There. And then we just have to flip everything around, plug in some stuff. Oh, I need to put coordinate systems on these. Actually, very important. One thing I don't know, it's interesting. Floating coordinate systems are bad. I agree with my professor on that one. But I think it's a little hard. He wants us to like put our origin as like a little dot, and so I like doing stuff like this where it kind of makes it so that the axes aren't totally like they aren't totally in the way, but it's hard on some of these. And like, oh well, I want to look for the axes, and then they're kind of, you have to trace them back, and kind of a rock and a hard place situation. Wow, we've been doing kind of zoom in, I'm not gonna lie. Maybe we can play some auction on. I've been trying to fix my colony that is not my entire brain shut off. My colony though, it's not the one I play on stream. There's like chlorine gas in like the base at this point. It's so scuffed. We have like no way. I'm like using hatches to farm for coal. It's okay. It's really, oh, what was I doing here? What was I doing here? I don't even know if I read this problem. I think I just like looked at it and I was like, what is going on? Let's see if we can make some progress. A spherical tank of a certain diameter is leaking air through a hole in its side. The air exits the hole so we're given a velocity at the exit of the hole, so we probably definitely want a control surface at the exit of the hole. And it exits at a density of that. Assume uniform mixing. There are no gradients in density of air within the tank. Okay, so it's incompressible, I guess. Please do the following. Develop a formula that describes the rate of change of average density within the tank. So no. Wait, yes, there is a rate of change, but it can still be incompressible and the density is changing. Oh, okay, so... Oh, that's fascinating. Because it's like, it's a gas, it's not a liquid. Whereas like a liquid, like the volume would be changing, but like for a gas, the volume is not necessarily changing. Okay. Well, let's make some... I don't know. I don't want to make assumptions yet. I think we need to figure out what we want the control volume to be. Clearly we want a control surface that exists at the hole. And assuming uniform mixing throughout the tank means that we can assume uniform mixing in a smaller part of the tank. So if we wanted to choose a smaller control volume, it's not like we couldn't. But we're trying to find the rate of change of average density, which kind of implies we need to use the full tank. Like, if I just take a piece of it, that's not going to be, like, the full tank. But I'm not liking the fact that we're going to have a sphere as our control surface, a control volume. I'm kind of not enjoying that. Partially because he said out loud today, we're not going to be using spherical coordinates in this class. Although, I mean, I mean, it's not like we couldn't integrate over a hole in the side of the tank with spherical coordinates. That wouldn't be that bad, I don't think. Because our radius would be the same, we're just changing our phi, phi, and theta. Sorry, I did a cardinal sin there. Maybe that is what we're supposed to do. Let's do that. Let's say that we have a spherical control volume. And I guess we just say that there's like a dA vector. Well, the dA vector is going to point in the same direction as our velocity is exiting, which is good. We like that. At least there's that. Oops, okay, my everything is crashing. Oh, there we go. I'm gonna leave this one here, because it's like not too in the way. Okay, we need a coordinate system. I'm gonna do spherical. Real. No toast today, sadly. How am I? I'm doing well. How are you? I'm sorry you don't have any toast. Or, I guess, maybe good that you don't have toast? Maybe toast is not the move today. Good, good, yeah. Go for some toast. How do I even define this? I guess I just say like this is theta. And this is phi. Do I really want to do this? I feel like this coordinate system is going to kick my ass trying to do anything with it. What are we doing? Yeah, man, use toroidal coordinates. I can't. We're doing some control volume analysis. So, fluids bookkeeping, essentially. Trying to keep track of the mass entering and exiting various volumes. I've never used toroidal coordinates before. I mean, I know what a toroid is, at least. Got that going for me. Oh, man, I don't even know where to start. Well, I guess we just start at the beginning. Probably a good place to start. No, you know what? We don't start at the beginning. We start at the assumptions. That's always where you start. Song doesn't start with do. It starts with assuming that the key of the song is sounds like polar coordinates, but in Africa. Look at the expansion for Laplacian. I'm googling. I don't even know what that means. Whoa! The Laplace expansion is an expression of a determinant of an n by n as a sum of weighted. Wait, I remember this vaguely. I vaguely remember this. I don't think I ever actually used this, but... Oh, wait. Wait, I know this. No, I did use this. Yeah. The weighted minors. Yeah. Wait, oh. This is like... I just looked up expansion for Laplacian. Toroidal... Thank you for letting me say the word toroidal so much. I really appreciate that one. That's a great word. Just so everybody knows what we're talking about. You know, this classic coordinate system. I really like the colors that they chose for this. So it's tau sigma phi. Tau sigma phi. Tau equals ln of d1 over d2. They're obtained by rotating a bipolar coordinate system about the axis separating its two foci. How do you even use that? Toroidal. Tortoise. The azimuthal? Azimuthal? That's a great name for an angle. That's crazy. That's, like, this is beautiful. Oh my god. Wait a second, you need to see this. We need to see this. What is this? What is this? What are you doing to get this? This is terrifying. For a vector field. Oh yeah, you know, just a classic vector field. Vector Laplacians. Oh, that's like psychic damage. So yeah, use this. Yeah, I'll use this one. I think my professor would call that one the relevant coordinate system of choice. I just think it's wild. It's a sphere. Of course you're gonna choose spherical coordinates. But he also said, like, literally he said today, you're not going to use spherical coordinates in this class. And I was like, I don't know about that, King. I think there are some spheres in fluids. He was like, sometimes it's relevant, but we're not gonna use it. And I was like, so, are we just gonna, like, do cylindrical coordinates then? I mean, I guess you could. It's not, like, the worst in the world. But, I mean, at that point, just use Cartesian, I think. Basically, only use spherical coordinates. If it doesn't have spherical symmetry, it's too complicated to me. That's so real. Oh, wait, okay, do we have steady flow? That's the first question we ask. Okay, they don't say that we have steady flow, so no, that's not an easy answer. We're trying to find the rate of change of average density. There's a rate of change in there, which probably means it's not a steady flow, probably? I mean, we're leaking air. Air is exiting. Okay, we don't really have to actually assume steady volume to be able to, or steady flow to be able to set up this equation. So let's start with the equation, and then we can go back to the assumptions. Although incompressible is an assumption we can make, I guess, or uniform mixing, which maybe isn't Ever seen a problem use the word please before? He's a very formal, polite guy. He writes all his own problems, I'm pretty sure. It's okay, you get a please in the problem statement, but then you also get a I'm not gonna help you answer the question. That's the kind of guy this guy is. But yeah, it's cool. Still no idea what's going on. Would you like to know what's going on, or are you content to just float in the sea? Because I can explain it if you'd like. Okay, we only have one control surface. Yes, please? Okay. So, I don't know how much you know about fluids, but these are problems about fluid flow. So this fluid is going to be moving, and fluids, we might be analyzing a liquid, or we might be analyzing gas. In this case, we're analyzing air, so it's a gas. But we're trying to attempt to use like dynamics, so like physics, dynamics and statics equations, but we want to be able to use them for fluids. But that's kind of hard, right? Because like we could just start from the beginning, derive the Navier-Stokes equation. No. We could technically use dynamics on like every single particle in a fluid, but that would suck. So we want to use a little bit more of a general way of describing it. So we have this thing called a control volume. This is basically just a space, a defined space, that we want to analyze the stuff going in and out of. So we say like, okay, we know that mass is conserved. So all of the mass going into this control volume has to equal all the mass going out of this control volume. And through that, you can prove a very general equation called the Reynolds transport theorem, which allows you to analyze different properties of a fluid as they enter. So like maybe we're interested in mass, maybe we're interested in density, maybe we're interested in temperature or energy or momentum. So that general formula is a little bit more specific here. Here we're we're trying to keep track of mass going in and out of this control volume. And the idea is we have one term that keeps track of the change in the property. So this is our time derivative, right? So if we're I don't know, maybe there's like more mass, or something's like decaying or something, right, into other stuff, and so that mass isn't counted as a fluid anymore. We'd be changing that with time. And then this is the control surface one, is actually just about how much stuff is entering and exiting our control volume. So we're saying like, okay, if we have this much fluid moving out at, I think the derivative is on the wrong side. No, this is it's the derivative of the integral. Yeah, it's a little confusing. It's the rate of change of this term. The upside down A is going in fluid. So this is a volume. This stands for volume. So we're going to be integrating over the control volume. So this whole sphere. This is our spherical tank. I've chosen, you can choose your control volume as whatever you want. Technically, you can choose it whatever you want. It might not be a useful control volume, but I've decided to choose it as the tank. So that's going to be, we're going to be integrating over the entire tank. We're going to be counting up all of the volume mass in there, and we're saying, okay, if that changes with time, that's what that's gonna... Your V with the line through it is triggering me? That's what he writes! It's because we have a velocity, and how are we gonna differentiate it from volume? That's the reason. Because velocity is a big V also. So little v's are for velocity. Write the V smaller. But look, that's a big V right there. I can't write it. They give it to me as a big V. The weird part about this one, I don't know if... We can do some stuff. We can deal with some stuff. Means for all. Okay, that's true. Since when the hell is it a big V? It's not. It's just a big V here. Some people are weird. I just do what the professor. I just do what the professor does, because he can read it easier. He writes control volume as CV like that. I know it means for all, but 1V. Okay, so our control surface. Well, we only care about one part, but I guess we could split this up into two. Okay, what if I split it up into two? What if I did a cheeky thing? No one's saying I can't have a control surface that's like this hole. See, the one thing I don't know about this problem is if the hole is flat or if the hole is rounded. And that sort of is important. I think it would be round, right? If you drill a hole in something, it's not making it flatter. I'll just do my calc 2. Oh yeah, calc 2 is great. I mean, this is like, hey, we got integrals. Calc 2. Is mass conservation a derived result? This equation? Yeah, Reynolds transport theorem basically comes from, okay, if we have some control volume, and it has this much mass in it at the beginning, and then we have a second state, where it has this much mass has exited and this much mass has left, you can figure out how much this mass is based off of the velocity. This is calc 7. This is applied, it's actually applied multivariable calculus. So, there are going to be some like integrals we use, but you could technically do it with calc 2. So like how much mass, basically the way they prove it is they make a little cylinder, and you say, okay, the area of this cylinder is, what if the energy is 0? Like, what if there's no energy in it? Well, then you have a perfect crystal at absolute 0 in Kelvin and nothing is moving. So there's no flow there. And it becomes a statics problem. It's a pretty boring statics problem. It's just sitting there. All of the molecules, everyone's dead. we say that like this length essentially can equal like a velocity, right? Like times a time. So then we can derive kappa. Then we can derive a little thing for this, and we take the limit, and it's a pretty straightforward ideal. Is it a derived result? I guess technically it would be a derived result then. Not exactly sure if you're looking for a more rigorous definition of the word derived result though. But you can derive it, yes, from that idea. It isn't from, I guess conservation of mass specifically is from that. Basically, the way the Reynolds transport theorem looks is it's a little bit more general. It says, what is it? New, not a new, sorry, eta, eta rho dv. And so when you have different intrinsic properties, then you can eta. Okay. You can switch these out, so like this can be temperature. Was mass conservation an assumption in deriving this equation? No, but conservation of like the property is. Not one number in this. Not yet, okay? Not yet. You put the numbers in at the end so you can get a model that works for anything. Because if I want to design a spherical tank and it's got a different diameter, or if I drill 2 holes in this instead of 1, then we can have something that works for that too, which is kind of fun. I'm gonna say that this hole can be described as the rest of the surface, but I'm just gonna draw it as like a hole. So I guess there technically is 2 control surfaces, because there's one where there's nothing where the hole is, and there's one where the not hole is. So we'll say CS1. That means I have to draw this arrow smaller. Okay. You guys know that's a V. Don't worry about it. It's right on the line. I don't need to draw the other area vector, actually. What if I just made the hole like larger just for me? There we go. Wait, so the other one is just going to be 0. Wait, so we're just integrating over the hole anyway. Never mind. I'm goofy. Because the other stuff, it's not going... It's an impermeable barrier. Mass is not... If gas just leaked out of everything, then we would sort of have issues with our things. I'm going to leave this just in this form because, okay, looking at this equation... I'm pretty sure we're gonna have to be solving for this. I don't know if we're solving for this whole term or if we're solving for part of it, but okay, triple integral. Wait, is it a triple integral? Wait, also this is not spherical coordinates. What am I doing? Where's my R? It took me a long time. Because mass is not in special relativity, so it's described that it is conserved in classical mechanics. Yes, we are assuming that these are classical mechanics, I will say. This is, there's another word for it. What is it called? It's like, I don't remember. There's a way of saying, like, basically, like, hey, sorry, this doesn't work for anything that's not, like, you know, really fast or really long or really large. Maybe it is just classical, but that's like what they say in physics. Another word for, let's see, like, fluid mechanics. I almost want to say, like, conservative, but that I don't think that's what it is. Okay, everything is crashing a little bit. Oh, it is actually crashing. Oh. Sorry about that. Oh no, we're good. I don't know. Like I was, is fluid mechanics hard? Maybe. what it's called. Alright, just pogged really hard. I'm just looking at mechanics websites now. Yeah, but it doesn't work for that stuff, unfortunately. I would love to also... It's also only 3-dimensional. It would be super cool to be able to do fluid flow in 4D. We don't really care about that too much, unfortunately. But here's what I say. Who doesn't... Can anybody prove the fluid isn't flowing in 4D? Checkmate, liberals. If we saying... Are we saying average density is, Oh wait, no, the density is... Okay, it exits the hole at unknown velocity and unknown density, so we can bring that out of this interval. And this is over the control surface still. You're doing 4D if you consider time a dimension? I don't as much, because I like... I mean, I do, but it's more fun if your fourth dimension is like, is a geometric fourth dimension. You can have hyperplanes and hypercubes and all that fun stuff. Let's do this dot product. It's always going to be positive. You like that? 4D. I love 4D. It's just super fun. I will never get over the fact that, like, it's not physically possible for us to, like, properly visualize 4D because we can only project things, like, into 2D accurately because we're in 3D. And so you can never visualize, like, up. So you'd have to, like, be in 5D to be able to, like, project 4D accurately. What update did I miss? Oh, yeah. You got the, velocity? Wait. Wait, it's just the area of the... Sorry, I got really excited. This is just the area of this little chunk. Yeah, we're on the new update. I do have to find the area of a... And I guess I could maybe simplify it. Then the equation with a dot product will work in a in 4 space. Exactly. Oh, cross product won't. Yeah. Yeah. No, it would work in 4D. I think a lot of dynamics stuff would work in 4D. Just realizing now that it's completely wrong. Like, any sort of moments would not work, but... I love that I don't even think I have to use this coordinate system. I mean, maybe I do for this bit. I still don't know what, is it even asking average density? Rate of change of average density. Ugh. You'd be integrating over a 4 volume and the boundary of a 4 volume? Yeah, but that'd be so fun. You know, it's just equations. Okay, so this is like, maybe I should just call it row 1? I guess they call it row exit. Okay, and velocity exit, and then area, I'll call it exit. I just call it area, because my vector's called that. Well, what have we got? Got something. How do we find average velocity? Well, if we want to find, like, average velocity, it could be, like, initial velocity, final velocity over the time. No, I lied. Why would I say the time? Over 2. That's an average. Wait, no, it would be over the... No, wait, I'm thinking. No, we do initial position, final position over time. Whoa, whoa. So I guess I could do initial density versus final density, sort of type thing, but that seems bad. Especially because it says develop a formula. And it says calculate a numerical value for dp dt. Okay. It doesn't really matter also where the hole is. That's kind of fun. Kind of interesting. It's gotta be something to do with this. Oh wait, I didn't explain the past thing. I figured it out. It was really easy. all you had to do was just... Okay, this looks hard when I do it. In theoretical physics, most of your integrals are over 4 dimensions instead of 3. Whoa, that's cool. I should check out theoretical physics. All I had to do for this was reparameterize it to 2 instead of 1. Which... Of course I had to do that. I'm going to be real though, when I took multivariable, the only reparameterization we did was in polar coordinates. And so it was very confusing to me because I was like, I don't have an R vector. I don't have a 3-component R vector. What are intervals? Integrals? An integral is just a way of adding up a bunch of little stuff. It's kind of like you're just saying, I mean, really all it is an area under a function to give you, not a function, an operator to give you an area under a certain curve. But in reality, that's just adding a bunch of stuff. Oh, you meant the V? Intervals. Seeing if Bradley said interval. I don't know what that's referring to, unfortunately. I mean, we break stuff up sometimes, that's an interval. Yeah, oh my god. This was so much easier after I don't know if this is right, but it's probably way closer to right than what I was doing before. I was running in circles so much, man. Where's the V? In the word? In the word, I'm pretty sure. Intervals, not integrals. Okay, here's what I should do. I don't know what they're talking about. I'm gonna go see in the textbook if they have a definition for average density real quick. They hide stuff in there, and I'm like, man, you said this in one sentence, and I read it, but I didn't read that one sentence. Let's check that first. And then... I'm using Pritchard Fox McDonald's 2011 Fluid Dynamics. Average density is mass over volume. And intervals like arranged numbers. Yeah, I know what it is, but I don't know if they have a different way of just like, hey, we do it this way for these kind of problems. Although I guess it's a known volume. Damie is definitely visiting his friend. I'm the visitor. Me when the air leaves the spherical tank of diameter. Wait, so okay, the rate of change of average density, I guess, would be the rate of change of mass over the volume. The integral of rho dv divided by the integral of dv. Integral of rho dv. I think it would be, it's dm. No, we need a mass rate. So the mass rate is a mass rate loss. I think this is steady flow is the thing. Can I say it's steady flow? I don't know, man. Is the flow changing with time? Let me think about it. Because this is our m dot, which is dm dt. Is our flow steady? Man, I just keep coming back to that. And then we would just do this over v. That would be, I guess, our... It's gotta be that. It's gotta be that. Like, just from contextual, like, what do we have? Where can we go? Let me see if I can find a problem where they do have a dt, just to see what... Okay, that one's a steady flow question. Okay, here we go. Oh, here we go. Never mind. This is exactly the kind of question. Let's hop over here. That's Paper Mario. Welcome everybody to Mario. We're gonna change this to... Okay. Look, we have at t equals 0, air begins escaping through the tank with a flow area, a valve, the flow area of that. Air passing through has that. And the density, this is exactly the problem he gave us. So volume of the tank, it contains air. So they're uniform but time dependent. Okay, so it's not steady flow. But it's uniform flow at section 1. We are not told that it's uniform in our problem, but I guess we can make that assumption. We probably should make that assumption. Wait, I did make that assumption. Whoops. Since the properties are assumed uniform, we can take the rho out from within the volume integral of the first term. Okay, so... Oh, okay. I get it. So it is incompressible. I just realized I still have big water down there. I mean, I guess it's not incompressible. I guess that's kind of incompressible. That is kind of what incompressible means, but I feel bad to say incompressible. Okay, let's not worry about that right now. Let's worry about this. Okay, so we say d dt of rho. Okay, let's assumptions. Uniform rho. Time dependent. Like that. And then we'll also say, I guess, uniform V at outlet at hole. At removable discontinuity. Okay, so then we have integral of CV, dV, and this, CS. Now we can pull rho out of this one too. And then VDA. Like that. And, well, we can... I'm pulling the whole thing out. B, E, E times A. And I just did the exact same thing again, but like... Fine. Okay, so we have that. Now let's see, so... Oh, we're chilling. We're chilling. ddt of rho times V. Look at this. Wait, so it kind of is what I was saying. I was like, this is the mass. This is the mass, and it's gonna be like divided by velocity. That's what it's gonna be. Yeah. So this is the change of... Because the volume's not changing, so if we do dt, then this is going to give us 0 equals d rho dt times v. I'm going to move this over here. And then minus rho e. Oh, that's so funny. Okay, so my intuition wasn't too far off. So... I don't know if that would be a partial or not. That's my one thing about this class. We haven't really talked about partials too much. Or like, we've done partials, but I don't know when we should apply a partial versus a non-partial derivative. There we go. Look at that. Easy. Easy, if you will. And I didn't even have to use polar coordinates actually at all. I mean, I guess I could for that AE, but... And then it says, calculate a numerical value in the tank for the instant in time when... Oh, we just did that. I never plug in any numbers. Are you considering x, y, z to be functions of t? X, y, z, like the coordinate system? Or velocity? Or... I don't think XYZ would be a function of time because, like our control volume isn't moving, or like, I guess R phi theta, or R theta phi would not be functions of time, because you can have a moving control volume, then you want partial. Okay. Cool. Well, but density would be, I thought density would be like only a function of time, right? Because we're saying that it's uniform, which means that it's not changing throughout the space. So I don't know. I mean, I guess it could be a function of temperature, but we're not really considering. I guess I should probably say like T is uniform as well. I don't know if pressure would make a difference. I don't think so. It's a function of one variable, then it doesn't matter if you use partial. Yeah. I think it's only a function of time. Well, that's swag. That's actually so swaggy. Oh god. let's take a stab at this one. Matters if you're considering the change over some path which is parameterized by t. Yeah. For sure. If we were doing a Lagrangian description of the fluid, then that might be more applicable. But we're doing Eulerian, so don't think so in physics. It's just like it's just a coincidence in court. That's so real. That's so funny. Oh god, I don't even know where to start. Well, maybe I should read it. Okay. You can see I drew the control volume and then I like got scared that I drew the wrong one, so I didn't draw it below. When immersed in a uniform stream, a 2D, thick, elliptical cylinder creates a broad downstream wake, as idealized in the figure. The pressures at the upstream and downstream sections are approximately equal. Good, that's going to tell us about density, I believe. Yes. And the fluid is water at 20 degrees Celsius. Oh, it's incompressible anyway. So if velocity is 0, by the way, just in case people are confused about the notation, the reason why sometimes we use v, sometimes we use u, you might see u, v, and w, are because our total velocity vector is usually called v, but our x component is called u, and then our other components are v, w. It's kind of weird. I don't know why they don't just say like x, y, z, but what are you gonna do? So if the initial velocity is 4 meters per second, and the length of the elliptical cylinder, estimate the drag force on the cylinder per unit width into the paper, and look ahead in your textbook at the definition of drag coefficient. I don't know what the drag force is, but we are probably gonna have to sum forces, assuming, which means that we're probably not going to have to only use conservation of mass. We're probably going to have to use conservation of linear momentum. Doesn't look like this is applying a torque, so linear momentum. Oh boy. Alright, how do we... where do we go? Let's draw our control volume first. How about we do that? Always a good place to start. The place you need to start, really. This music is so accurate. This thing is locked in combat with me. Okay, where do we not need to care about? We don't really need to care about the top and the bottom. And maybe we do need to care about. Can you prove that momentum is a conserved quantity? So I think we didn't actually prove. Okay. Let me think about this. So, first off, you can prove that it's conserved through like dynamics, right? When we say that that's not momentum, mv, we can prove that this is conserved through, I think, like conservation of energy and conservation of mass. But the way that we are using the Reynolds transport theorem in general is by saying, okay, we have a property of some liquid, like let's say it's a momentum, and then this is our like external property, and then the internal property is like that per unit of mass. So we really are summing a lot of like velocities in these integrals for the internal sort of side of this, because we look like we're in the fluid and we're like looking at the fluid. We're not necessarily really looking at the total mass of the fluid. It doesn't really matter to us because we're integrating over it. But I think you have to sort of assume for this that these things are already conserved. Because really you can only do this Reynolds transport theorem with like temperature and energy and angular momentum and linear momentum and mass. So I mean, I think it kind of comes from the fact that you are saying that this thing is going to be conserved because of classical mechanics. And you know, when you start to get into places where it's not necessarily conserved, then it's not like you can say that anymore. Ooh, okay. I'm gonna choose a coordinate system real quick. It's gonna be the middle. I'm gonna do the middle because that wake that it gives us is symmetric, and so we'll do. I like that. Okay, we need to do some area vectors, so we'll put this one over here. And the velocity is coming out this way. And this way. dA2. And our velocity vector is going in. How did I write V2? Oh, it's because I'm too used to labeling my... Right. Okay, well we have to start with conservation of mass. This can't work with gravity if you require momentum conservation. So, okay, conservation is like, when I say conservation, it's not necessarily conservation as in like it's going to equal the same thing, right? Because in this sense, this cylinder is exerting like, you know, normal forces on the water, and that's changing its flow. So really, like, conservation of momentum is we are accounting like for the fact that forces are causing this. So it's not like saying like it's exactly the same at the beginning and the end. Otherwise, we would have a lot of easier problems. So I'm pretty sure you can work with gravity for it. You just have to like, if you're working with gravity, you know, it might depend on the problem, but you might want to use like energy or something else if it's something like that where you could do potential energy. Yeah, but this is a forces problem. But we're going to start with conservation of mass because mass is conserved. And if we don't know about mass, then we can't really do anything else because we don't really know how much mass is going in and out, and kind of need that to do stuff. Okay, do we have a steady flow? It's a uniform stream. Is this flow changing over time is the question. I do not think so. Like, if I think about it in my brain, if we just keep putting uniform stuff in here, like, it's not, unless we move the cylinder, it's not gonna change with time. Like, obviously, if we were filling this up, you know, it would be different, but then you also wouldn't have a uniform, well, you could have a uniform stream, input stream. Okay, so assumptions. Yes, it's incompressible, like that. Maybe there's something else we can assume later. Temperature isn't gonna matter, or it's not the main focus, I guess. We don't have any like thin gaps to worry about. Let's go for it. We're probably gonna have to draw a free body diagram of the cylinder at some point, but let's maybe just start with mass conservation. I feel like that's good. So we have that same thing. 0 equals d dt. This term is gonna zero out. CV. Because we have steady flow, so the flow is not changing. Now, okay. We have two control surfaces. One of these control surfaces is relatively straightforward. The other one is slightly less straightforward, but not really that unstraightforward. Ah, it's interesting. So the length of it actually translates to the length of that. That's fascinating. Okay. So control surface 1 is our one on the left, the harder one. The row 1, I guess it's just row. V1 dot DA1. Control surface 2, row V2 dot DA2. Okay. And we're probably just gonna end up with like m dot 1 equals m dot 2. But that's still useful. You still gotta like say that. You can't just be like, ah yes, mass is conserved, trust me. Like, no, I don't, sorry, I don't trust you. So we can pull these out, and they're gonna cancel. Like that. And we'll say, okay, V1 is a little more complicated, but positive. You don't trust me? Okay, Angel Thump. Is that Angel Thump? What emote is that? Bible Thump. I was close. Is that Isaac? Binding of Isaac? I need V1 still there. And then plus, I guess just V2. A2. Minus. Okay. I like it. Hey, well, this is useful. I mean, we can figure out the mass. Well, I mean, we can figure out the volume flow rate. It's not a mass flow rate; it's a volume flow rate of this easily without having to like integrate this. I'm gonna leave it like this for now. Like Q2. The volume flow rate, by the way. Like how much stuff is flowing through the volume. Or that surface. Okay, drag force. I don't know how to do that. I think it's a linear momentum conservation. But that doesn't really mean a whole lot to me right now. Momentum equation. Here, wait, let's just go on an adventure. We now wish to obtain a control volume form of Newton's second law. We just use mass conservation. Yeah, so we're saying Newton's second law is F equals the change in the momentum, rate of change of momentum of the system. Linear momentum of the system is V dm. I'm okay with that, yeah. God, I love calculus. I don't know if that's being facetious, but I actually do really like calculus. I think when you get to use calculus to do other stuff, it starts getting really cool. It's like, it's generally not a lot of hard calculus. It's usually kind of easier calculus, and you just get to feel like a wizard, and I like it a lot. Okay, so we have the body and surface forces that we're accounting for. So the control, yeah, so this is Reynolds transport theorem. We have again, to derive the control volume formulation, we set n equal to p and n equal to v. Yes. See, look, they use v in this too. They use the upside down. It's like v with a line through it. Then we have the PDT of the system, which is going to equal our forces at the end. Oh, they tell us that. Equals d over dt v. Okay, so we just switch out everything for v's, essentially. Pretty chill. For cases in which we have a uniform flow at each inlet and exit, we can just multiply stuff, but whatever. We can do that when we figure it out. There's a non-accelerating control volume, because we can we can say that our control volume like moves if we want to. You don't always want to do that though. If the total force acting on the surface volume leads to a rate of change, momentum within the control volume, and or a net rate at which momentum is leaving the control volume. Must be a little careful. Applying 4.17. Oh, we need to label external forces. Oh, wait, we have to... Oh, no. Wait a second. Ooh, wait, that's a little goofy. Whose hand is that? What is this? Water from a stationary nozzle strikes a flat plate. They are not holding that. What is this diagram? Oh, they're trying to hold it up? That's so bad. Okay, we choose a coordinate system. We must choose a suitable control volume. Two possible choices are shown. It's assumed to leave the control... Okay, this is weird. Don't we want to use... Oh, okay, but how... Wait a second. Wait. If we... So... Don't you always hold things by stabbing them directly in your hand sideways? Yeah, I'm actually just made of mush, and so when I stick stuff in my hand, it just kind of stays there. I don't know why everybody doesn't do that. Really the better way of holding stuff. Okay. Oh, we can't do this. We have to choose a different control volume. Wait a second. Wait, I just big-brained an idea. Life is so much easier when you lack bones. Yeah, my bones are everything, actually. Everything is a bone. Don't ask how that makes sense. It does, I swear. Okay, are you ready for the big brain move I think might be the answer to this? Bam. That way we get the inlet and the outlet, and we can still do this. I think that might be it. Now, we'll have to, like, you know, mirror it. I think that's it. Okay, let me be able to draw an ellipse. There we go. So I guess the forces, but the forces are like there's... Oh, we need an equivalent force, I guess. There's like a pressure gradient? No, I'm kidding. There's not a pressure gradient. I don't think so. There is there's forces everywhere, though. Forces are coming to get ya. That's what's happening. I don't know, there's like one force. Does it really matter? I mean... Oh, wait, but that means I need to have a velocity up, too, huh? It's like, up at the... If I have a force up at the top, is there... I don't know, this is so complicated. Okay, we need to go back to the hand example. The boneless hand. Okay. The steady flow, incompressible flow, uniform at each section where the fluid crosses CV boundary. Okay. Evaluating, so regardless of our control volume... Oh wait, they didn't do conservation of mass. Bad. You always do conservation of mass. Important. Evaluating the momentum flux term will lead to the same result. Oh, they're not actually doing it. Okay. Control volume has been selected so the area of the left surface is equal to the area of the right surface. Sure. The control volume cuts through your hand? Bro, I don't have a hand anymore. It's so rude of them. Jeez. Oh, they just put some stuff in here. It's just, like, floating around. Funny. Atmospheric pressure acts on all surfaces of the control volume. Oh. Okay, I don't have to worry about that right now. Guess. Know that the pressure in a free jet is ambient. Oh, sure. The distributed force due to atmospheric pressure on the vertical phase. So the body force... There's not weight for us, because, like, we're looking at the top-down view, luckily. We are looking for the horizontal force. We're at the x component of the steady flow momentum equation. This looks like a lot. Oh wait, so they actually managed to do it. The control volume has been selected so the areas are left surface and right. Wait, how did they do that? Wait, what? Wait, how did they actually manage to do that? Didn't they select it so that this is like a, how do they know how much area that is? I mean, I guess they just figured it out. Well, it would be this. No. I might have to skip this one. I think a momentum one. I guess I could ask him to office hours tomorrow. Good idea. I don't have class till Wednesday. Let's see. Or two. Maybe take a crack at one more. Oh god, what was I doing here? Oh, wait, we actually might be able to do this. We might be able to do this. Oh look, I wrote. Oh, you can't see it. Look at this. Changing direction. Forces happen. Good job, past me. I also remember that. Okay, this is a rocket problem. This problem where a big funny hammer falling, then I think I would be more into it. That's all I'm saying. Kids these days. Teenagers these days. I don't know why I said teenagers. I'm not a teenager. Kids these days, they're always on their big hammer. Kids love big hammer more than book. It's me, I'm kids. What is this? Okay, a test stand for determining the thrust of a liquid fuel rocket. Okay, it's liquid fuel. Cool. Liquid propellants. Enter at section 1. Ooh, we're given a mass flow rate. That's nice. A mass flow rate, a velocity, and a pressure. Okay, so if we're given mass flow rate, velocity, pressure, we can find the area. Which, whatever. Inlet is very flexible, and the force it exerts on the rocket is negligible. At the nozzle end, exit, so a nozzle is gonna accelerate flow. The area of the nozzle is that, and the pressure at the exit plane is that. Although it is not apparent in this figure, you can assume the nozzle is designed such that the velocity at the exit plane is in the axial direction. Sure. Furthermore, the arm lengths of the leveler are not labeled, but to consider the short and long arms to be for whatever. The flow is steady. Wait, let's go. I can put they told me it's steady. Let's go. Oh, giant win. I love it when the flow is steady. Me when the imposter is sus. Me when the flow is steady. That's my grin of excitement. Okay. Develop an expression in variable form that relates the total thrust force developed by the rocket due to the nozzle exhaust options. This is a flow rate question, and then we do momentum conservation as well, which is funny because none of these are particularly tricky. They're just sort of a little hard. Like, they're not even really that bad. We are gonna have a force here. This is a normal force. From the... Okay, we have a normal force from that, and we know that that's gonna, like, be given as something, and then we also have a normal force from the wall. I think those are really all our forces. We do have a weight force, which I guess is probably also gonna come into play. Well, I guess we have a weight, mg. Probably should just say F weight. N2 vector hat. Would it be 2 normal forces, or do we think, what do we think? We're gonna go with 1. It might be like 1 here and 1 here. gonna say it's that though. N2 can be found. Note, I'm just gonna, I don't know. Can found. A little depressing music. Me when I go back to my sad troll volume. I have no unknowns. My whole life is defined. I can't even analyze it. Cries so sadly. Small violin plays in the background. But that's not us. We've got, how many unknowns do we have? Let's see. I don't really think the weight is gonna matter, I think let's maybe get rid of the weight. I don't think the weight is really gonna matter here. It's also a volume, and I'm realizing now that it's kind of silly to give I'm not doing a free body diagram of the thing. But these forces are important. There might be a normal, no, I don't know. Okay. Let's do analysis. And conservation of mass. The only thing we know how to do, which is okay. Okay. A0 equals... So we're not changing with... Are we changing with time? No, not really. Right? That would mean like either our density is changing with time or our velocity is changing with time. And we're gonna say it's not. The liquid? Okay. I think it's incompressible. It's like Mach number. Mach number is velocity over speed of sound. Like 30 over 300 at 0.1. It has to be less than 0.3, so that's going to be incompressible. So we can get our densities out. I'll still write it out, I guess. No harm. Alrighty. Oh, density. I got too excited about the music. 0 plus control surface rho. I'm gonna pop the rho out. I'll leave it. I'll do a little of that. And then oh wait, let's do control surface 1, I guess. Why did I write V2? That's V1. That's V2. V1 dot DA1. Rho V2 dot DA2. That out. These will cancel. Cool. So I think it said it's uniform, right? Well, so the velocity at the exit plane is in the axial direction. Now, it is a nozzle. I think it's supposed to give uniform flow. Is it giving uniform flow? Can we say that? I don't know. Does it really matter? This mass flow... Oh wait, mass flow rate. Wait, no, don't bring this out. Oh god. I'm gonna actually get rid of this and I'm just gonna give it mass flow rate instead. Do we want the area or do we care about the... Oh, we definitely need the velocity and the pressure for the linear momentum stuff, so this can be m dot. That's nice. It's just like a shortcut to make the problem shorter. Slightly. There we go. Now, I think velocity would be uniform, but I'm not sure. This velocity at the exit plane is in the axial direction. Maybe it's a badly designed nozzle. I don't know, they don't say that it's uniform. Maybe all nozzles must be uniform, otherwise it doesn't get to be called a nozzle. Kind of a funny thing to say. Generally, that's not really how it works in engineering. Okay, zooming in and out isn't gonna help. Okay, so we have an area of the nozzle, and we have pressure. I guess we kind of do need more information, huh? So we probably get that from this mass flow. Because we can get, we can solve for a V2, I guess. Okay, let's just say that it's uniform at the surfaces of the control volume. Whatever. Live and let die. I don't know how that expression goes. Uniform V at CS's. What would that mean? That would mean that negative m dot equals oh wait, no, this is negative. It's a dot product. So m dot equals the density, which we can get, I think, through the mass flow rate of the other one. Or do they just give us a density and I'm like goofy? No, they don't give us a density. Okay. Density, it's water, right? Oh wait, no, it's not. It's no, definitely not. V2 times A2. So V2 equals m dot over rho. M dot, I think the rows will cancel out, right? It'll be like rho. Here, wait, let me like actually finish writing it out. Jeez. Okay, so it's like rho V1A1, which we have all that stuff because this is gonna go away. Oh, huh, that's a little interesting. All right, there we go. We got a velocity. Look at that. Look how great. Look at how useful this is. Actually doing conservation of mass, giving us stuff we don't know. Instead of like the other one where I think you technically don't really have to do conservation of mass, but he says always do it, so what are you gonna do? Somebody tells you, hey, I'm grading you, you always gotta do this thing. You're like, I guess I gotta do it. I promise, guys, I won't make you random things. I'm sure this is gonna be one of those things where I'm like, yeah, I just do conservation of mass every time. Let's see, it's 3:48 right now. I guess we could look at one more. I know I'm not finishing these, but you know, I want to ask about conservation of momentum before I try and just like lie in there and do it and then do it wrong and then have to redo it anyway. Usually how it goes. Where is this thing? I have to go and find it now. Are there any more fun ones? Are there any more funny little fun things? Probably not. They're probably all serious problems about rockets and ducts and... Oh, wait. Okay, it says this. You might find many of these problems more challenging than the typical textbook problems that you are used to being assigned as homework. But bear in mind that nearly all the problems that follow are from alternate undergraduate fluid mechanics textbooks, so they are an appropriate level of rigor. It's fine. Ooh, okay. Okay, we have this. I'm deciding whether I can show it. I'll show it. Why not? Whatever. Who care? Oh yeah, we're good. Okay, so we have a flat plate attached to... We can choose one of the two. What that says. The flat plate is attached to a rolling cart. A free jet of liquid is directed at the plate. The jet strikes the plate. and plate splits the jet equally. Neglecting and aerodynamic resistance, and neglecting viscous effects. So, okay. Derive an expression for the power required to move the cart with a velocity u toward the jet. Okay, so we could figure out how much like force we need this way, which I guess power is like energy per time, right? So that would be related to velocity. Velocity is a movement per time, kinetic energy, that kind of thing. Or, however, now realize that the liquid jet can be used to propel the cart with a constant velocity u away from the jet. The speed at which the cart moves is still dependent on the force F that is applied. We can think of this force, using this force to extract power from the jet. What speed should the cart be allowed to translate in order to extract the maximum power from the jet? Oh boy, okay, so we can either figure out how much power it takes to move it, or when it's moving, how much power it gives. They're pretty similar. I don't know which one would be better. What do we think is harder? I feel like... I feel like 8 is a little easier, because you can do kinetic energy, like, after you get the velocity. It's like, we kind of got the velocity on that other one, right? Like, it was conservation of momentum. It's a little different, because we're gonna have to accelerate this and figure out stuff a little bit differently. I feel like A is a little harder. They're both about the same, honestly. Let's maybe try A. Okay. Let's see, wait, what other problems are there on here? Oh, additional problems. Oh. Look at this. This is crazy. I don't know what this is. Submersible pump was used to draw water out of a tank and force it upward through a copper tube and nozzle. The jet of water issuing from the nozzle, directed vertically upwards, struck a thin, horizontal, circular, flat target plate. A load cell measured the force on the plate due to the water jet. Okay, so you just shot some water up in the air. Sure. And you measured it. An inline flow meter pressure, volume, flow rate. Wait, what is this? This is just you shot some stuff up in the air? How is this hard? What is this? Nozzle exit diameter, sure. Develop an expression for the force imparted by the jet of water on a target with arbitrary deflection angle. Oh. Arbitrary deflection. Wait, why would you change the deflection angle? Where? I don't know. This is not something we actually do, but it's kind of interesting. Cool. Cool story. Cool story, problem set. Thank you. This problem is provided for students who want a real-world problem and is unique from all the other problems in the assignment, as there is a data set you can use. Sure. That's cool. I'd be down to try that at some point. Maybe we try that on stream later, though. Tomorrow I'm probably gonna do... yeah, I'm probably gonna do some of these. I don't know, actually. Maybe Wednesday will be my... What is Wednesday for me? Oh yeah, Wednesday could be my grind day. Why is this problem, like, dusty? It has got, like, dirt on it, man. Bro, what is all this? What is all this? Bro, clean the dust off. It's not been that long. Okay. Unit control volume. What do we think? What do you think is a good little volume here? Well, let's just use the one the book uses. Ooh, but we could do a triangle. What should we do a triangle? What do we think? Triangle's pretty cool. We know we don't want one surface here. Well, okay, the book showed that you could actually do it with 2 different control volumes, but I feel like this one is more... makes more sense. We don't really care about the exit velocity, like where it meets up, but we do know this. But okay, if we know this, I guess it might be better to just do this. The most, like... It's so extra. I don't know the exit, I don't know the velocity. What do I do here? I don't know that velocity. Oh no, because I know that this isn't, like, flow isn't gonna cross there and there. Okay, we know we want one here, definitely. But we want it, like, at this surface. Like, we want this area to be here, you know? I mean, I guess I could just literally... No, it would suck to do what I was thinking of, which is just, like, literally just draw this over and, like, make a triangle, but that would be so bad. That would be so bad, because we don't know, like, the angle of the velocity. Yeah, no, that's not happening. I feel like it has to be this. But then we have to figure out, like, this and this. Maybe we can figure that out because it splits in half. Exactly. It splits the jet equally, so we'll probably be able to say, like, something about the masses being equal. I don't know, maybe. Oh, the Boggly Tree is such good fluid dynamics music, actually. Okay, there's our volume. Oh okay, control volume. Control. Oh my god, I can't spell. Fuck. There we go. I'm getting a little goofy, as you can tell. Control volume. Okay. Let me check one thing. Okay. So we can do... Oh god, that's too thick. I don't even know what angle... That's okay. We'll figure it out. Ooh, that was bad. It's okay. That's like, it's close enough. That's good and fine. Fine and good. And good and fine. Okay. That looks really goofy. Okay, so, there's an area here. And there's a velocity in here. Given as v0, I guess. Maybe I call it a0 then. And... Oh, we actually know that there's... Yeah, there's actually not going to be any flow. I don't know why I was thinking... V1 and V2. We're going to call them V1 and V2 just for now. VA2. But, yeah, there's not any flow, like, into the cart. So... Okay, coordinate system. I think we do... Oof. No, it's okay. It's okay because they're just gonna be... Yeah, they're all in the same directions, so... Let's do this. Middle of the plate. So at least we can get some symmetry going. We'll call that X, we'll call this Y. Maybe? I don't know, maybe this is Y, that's X. I feel like this is X and this is Y, because if I had this being Y, then X should be over here, you know? Okay, it got a little big up here, let's move that. Alright, assumptions... You got one, is it steady? I don't know. That's a great question to ask. Well, one thing we can assume is it's, let's say it's incompressible. Because I don't really want to deal with it being not incompressible, but also I feel like it's a liquid, it's fine. Would it be steady? No. Probably Not, because the cart's gonna move, right? So not steady. Like, if you look at this in one screenshot, then that, or snapshot, whatever, like, the cart's gonna be moving forward, so it's not steady. Okay. Now maybe let's do some analysis. His favorite. Oh boy, we get to ride the train again. A little dinker on there. Okay. We'll just do this and then I'm gonna wrap up for the day. Okay, so the DDT we can't really get rid of. But that's fine. That's kind of gonna be a pain, actually, now that I think about it. I don't want to think about it, it's fine. We're gonna forget that it exists, so. Is the control volume... Oh, the control volume needs to move, I think. How do you do a moving control volume? Oh, shoot. Yeah. It should move, and then... we know that the V at the inlet is, like, gonna be the same. Oh, I don't know how to do this one, but we're gonna set it up anyway. So I guess we have control surface 1, or 0. Rho can come out, V O dot DAO. Negative, and this rho can come out. Plus control surface 1. Now the control surface 1 and 2, I want to say they're the same. Like velocity. I'm gonna just say +2. Now they're in different directions, but... you know, I feel like this is what my intuition is telling me. V2 is closer to me in my visual line right there, so it's getting this one. And that's that. That was pretty good. Honestly, we did a lot. I feel like there's some solid stuff in here. Well, it's not solid, it's fluids. Okay, sorry, that was a bad one. But yeah, like, oh, this one, don't look at this. This is sad. This is sad. I could redo that one easy. This one, wait, no. This one, I'm happy with this one. This one's great. It's just a great, simple little problem. We made some really good progress on it. Yeah, so that's gonna be it for me. I'll be back. I'll probably stream Wednesday. Because I gotta do lab stuff tomorrow. Which I'm not gonna be feeling great after, probably. But yeah, I'll be around. We might do... I don't know what we'll do on Wednesday. Maybe we'll do... I have no clue, actually. It could be anything. We could just play games, maybe. I don't know. If this isn't done by then, I'll probably do this tomorrow. Yeah. Thanks for hanging out, everybody. I'll see you then. Have a great day.